Okay, this video is a quick little introduction to work done, how we calculate work done. And I'll start out with a simple example that doesn't really involve calculus, and then we'll talk about why we need calculus. So the idea here is that, well, first of all, you need to know the work done is basically, it's a calculated, you calculate the amount of force it takes to move something, and then you multiply that by the distance that you spend moving it. So a simple example, let's say we got 200 pounds here, this little forklift. Get impressed with my drawing. Put a hat on the worker that's lifting this. Okay. So so he's going to lift this 200-pound weight, and let's say the tractor's lifting, not him. The tractor is going to lift it 5 feet off the ground. 5 feet off ground. So that's very simple. You just take the force it takes, and the force it takes to lift this, there's 200 pounds based on the force of gravity is holding this thing on the ground, right? There's 200 pounds of force holding on the ground. So to resist that, to get it to move, I have to overcome those 200 pounds of force that's pulling down. So I have to apply 200 pounds of pressure underneath this block to lift it, and I'm going to lift it 5 feet off the ground. So to calculate the work done in this situation, it would just be 200 pounds times 5 feet, and we get 1,000 foot-pounds. Now that's actually it is a weight unit of work. There's also, you can measure, there's other units, but that's one of the units of work, and it's not foot per pound, it's foot pound. It means you're multiplying the units of feet by the units of pounds. So that's the idea of work done. Now, why would we need calculus for this? Well, the idea is if you're lifting something like a weight, let's say the same tractor is trying to lift a length of chain. And let's say it's coiled up on the ground or whatever. So in the process of lifting this thing, chain hooked around here, I'm getting a chance to show off my drawing skills here. Okay, so as he's lifting the chain, when he first starts lifting the chain, we'll do little stages of this. When he first starts lifting, there's only a couple of links that he's lifting because everything else is sitting on the ground. So the weight that the force that's required to lift it is not very much at all. It doesn't take much at all to lift a couple of links of chain off the ground. But as you get more and more links in the air, the weight required to lift it, or the force required to lift it, gets stronger and stronger and stronger. So we can't just multiply the sum total weight by the distance, because let's say the chain weighs 4 pounds per foot. Really heavy chain. Okay, so if it weighs 4 pounds per foot, and let's say it's 10 feet long, the total weight of the chain would be 40 pounds, right? Because you take 4 pounds per foot times 10 feet, that'd be 40 pounds. But he's not lifting the full 40 pounds, the full 10 feet. So what we're trying to do is get the chain completely off the ground and then stop. So I'm going to lift it a total of 10 feet, but not every link is being lifted 10 feet, and that's why we need to do calculus, because the force that's being applied to different links of the chain, or different section of the chain, is different. Okay, so so again, when we're going to use integration to do this, and we have to come up with some kind of anytime you're doing integration, you have to ask yourself, what is the little pieces that I'm adding up? And that's the hardest part about these problems, is figuring out what the little piece is. So let me help you. I did some colors here. I paused and put some colors in there. So think about the yellow links. They're not going to be lifted hardly any distance at all. Compared to, I'll get some more, get some other more colors here. Let's do light purple. Look at this light purple up here, right? So that one's going to be lifted the full 10 feet because it's at the top, right? Whereas this little yellow section is only going to be lifted a little bit. So that's one way to look at the how we're breaking it up. So we're going to take this little section and we're going to figure out how much weight it takes to lift that section, and we're going to multiply it by the distance that that section moves. So we're going to have down here, we're going to have our force and then our distance. Okay? Now, the distance, I think that's the easier part, so let's talk about that first. I need to break this up into a number system, so what I'm going to do is call this 0 and call this 10. So the distance, the farthest distance any chain is going to move is 10, and the smallest is 0. So if we call this maybe h or something, or just x, we'll just say distance along the chain. So the part of the chain, so x will be the distance from the part of the chain that's hooked to the lifting tractor. So you can see the distance. You know, the distance at the very end is going to be that guy's only going to be moving a little bit. This guy up here, a ton, is going to be moving the full 10. So what we're going to do is we're going to do 10 minus x, because that way when I plug in 0 essentially for the first part of the link, he's going to move the full 10. When I plug in 10, he's going to move hardly any at all, 0. So that represents the distance that each of my little links are moving. Now the force is going to be 4 pounds per foot times the distance. Well, remember the distance, like usual in integration, is we have some little change in, I was talking about links, but we're going to get it even smaller than that. So there's going to be some little change, some d and x. So my force is going to be 4 dx. So if we rearrange this a little bit, it would make more sense to go 4 times 10 minus x. Put the dx out here. So then just the limits are going to be from 0 up to 10. So again, I want to make sure we're clear on this. This is the distance that the force is being applied. This right here is a part of figuring out the total force, because we're taking 4 pounds per foot. So this chain weighs 4 pounds per foot, so we have to multiply it by the number of feet to get the force for that section. And that's where that little dx comes in, because we're taking 4 pounds per foot times this short little distance of chain. So then we're integrating across x, and remember x we said was the distance, was the length of the chain, where 0 is the part that's connected to the tractor, and 10 is the end of it. So so that's the parts that connect to the tractor goes the full 10 feet. The part that's the furthest from it just barely gets lifted off the ground. So that's an example of why we would need integration to find work done, because the work is either the work is changing, the force is changing, or the distance is changing. In this case, we had the same force all the time, but different sections of the chain were moving a different distance. So, and there's some other examples, but I think I'll save those for the next video. Maybe I'll do one more of these. Another example kind of like this, where this is a classic example where you got a building, and you got a banner that's hanging off the building, and we've got to roll the banner up. So we're trying to calculate the work done. So let's say across the top here it's 15 feet, and this distance here is 20 feet, and the banner weighs 4 pounds per square foot. Okay? So this is not a force. This is a way to find force, though, because it's 4 pounds per foot, and we need to figure out the total force, of course, would be 4 pounds times some square footage, and that would give me just pounds. So we have to calculate the square footage of the banner. Now, of course, we can't just do the full square footage. That'd be 20 times 15, because once again, different lengths, the whole banner isn't being moved the same distance, because we have to multiply the force times distance to get work done. So we know this is going to be 4 times something, right, times the distance. So this is distance, this is force. In order to get the force, we need to multiply 4 times something, right? Okay? So once again, as we've done in a lot of problems, we need to figure out strips of banner, just like we found out lengths of chain that are the same, that are moving the same distance. And notice in this case, we're going to take little rectangular slices, just like we did back at the very beginning when we were looking at integration. So this whole stretch of banner is going to be moved the same distance, and this whole stretch of banner is going to be moved the same distance, etc. So we need to find out the force applied to this strip of banner. And of course, that strip of banner is just going to be 15 feet by some little change, right? We could call it dx. And that would be the area of that banner. We have to multiply that by 4. So this is going to be, in place of force, we're going to go 4 pounds per square foot times 15 dx, because 15 would be the length and dx would be the width, and 15 times dx would give me the square footage of that strip. And of course that's the same for every one of these strips, right? And then we got to calculate the distance moved. So if we're calling this x, we'll call this up here, we could call this down here 0, and this up here 20, and this is the x variable. So that means we're going to integrate from 0 to 20, and of course at 0 I'm going to move the full 20 feet, so that would be 20 minus x. When I'm at 20, I'm only going to move 0 feet, right, because I'm already up there. So this would be the distance that the strips of banner are moving. So again, let's say this is at 10 feet. No, let's say this is at 15 feet. So that distance right there is 15. That means that if we're calling the bottom 0, that means my x would be equal to 5. If we put 5 in there, you see that the distance that's being moved is 15. And again, we're integrating from 0 to 20. So if we write this more proper, 4 times 15, of course, is 60. So that'd be 60 times the integral from 0 to 20 of 20 minus x dx. So that's an example when you're pulling something up and the force is kind of the same, or at least the force per something is the same, but the distance that each little section is being moved is different. So I showed you a chain example, and I showed you the banner example.